Okay, let's start. Welcome back, everyone. So, I mean, still January 2026. That seems wrong.
We'll still live in time.
Yeah, I know.
We're ready for the year.
I keep updating the lectures, but I didn't change the year. Okay, so just to make sure that we understand what's going on again. Today's like the first lecture was kind of okay, loosey-goosey, like all those general things. This one gets a little bit more concrete, but it's still pretty high level. But I promise you, and this topic probably will take us to two meetings, so we'll probably end next week. But still, there will be like some source code even today, right? But in general, we'll gonna dive into the details pretty soon. And like as I said, we will be reading the source code of x86, right? So just bear with me for a moment, and you'll see all those juicy details pretty soon, right? So today and next time, just because it will take us a little longer than one lecture, our plan is to talk about the interface of the operating system, right? Let's just quickly recap, just to get everyone on board with what's going on. This is what we discussed last time. We said, okay, if you want to build an operating system kernel, like imagine you yourself build one, and it seems like, okay, sure, it will never happen in your life, but in practice it might, right? So especially today when like hardware is changing aggressively, people are, I know multiple people, I mean, of course I'm in that field, but I know multiple people who build their own clean slate from scratch operating systems. And you say, look, but maybe Linux has captured the market, or Linux/Windows/whatever. It turns out, no, they're like automotive market, like they deploy their own operating systems, like in your car. They do all sorts of things, like embedded devices. So it can happen, right? And imagine for a second, you're building a new kernel. Just you say that, your end goal as usual, just to write a program, be it like a screen in your car, right? Or something on your wristwatch. You say, okay, what are the main things I have to implement to get something running as soon as possible, right? And you say, look, wow, this piece of software will be designed to run applications, meaning that it will share the hardware, like one instance of the CPU, one physical memory across multiple programs which you're running on this device, right? And in order to get up to speed and program against this low-level hardware interface a little faster than like forever, you say, look, I will be developing some layers of abstractions to make sure that, I wrote them once and other people on my team can quickly program against those interfaces. And that's called device drivers, right? The kernel. And you say, look, but we want other services. We want memory allocation. We want, I don't know, printf, sending packets, reading files. And so you start writing those services. I wrote a couple of systems, and I mean, you can argue whether they make sense, but some of them don't have file system. It's not the very first thing you usually need, but you will need it eventually. And then at the core of it, if you want to enable ecosystem of applications in some meaningful, secure, and reliable way, you need to think about isolation and controlled communication, right? Because everything has to be, in the end, everything has to be locked in, and then yet has to communicate, right? And roughly speaking, this is what you will end up building, plus whatever. Like we talked about scheduler, and most likely your first iteration of a system will look something like this, and it's a typical example of a modern kernel, like Linux, Windows to some degree, Mac OS. I mean, they all deviate slightly. This is like, if you want to be more specific, this is Linux, right? So you have this layer, which people historically call the kernel or operating system kernel. You have user applications, I mean, like Shell, Apache Web Server. They communicate with the kernel, which provides those services through a layer of system call interfaces, right? System call interface. Typically, you have something like libc sitting here, which provides a high-level interface to low-level invocations of the system call interface, because they're a little nuanced and they vary like from hardware to hardware, but in general, like they're close, right? And inside you have all the things like file system, scheduler, memory manager, network stack, device drivers, which talk to hardware, stuff like that, right? So you will end up doing something like this. And every time when you start from scratch, and again, I started myself from scratch, and I have friends who did the same in industry. You start thinking about what this interface should look like, right? You're starting clean slate. You say, look, I have a specific goal. Maybe I want to save as much power as I can, because maybe my device doesn't even have a battery. It harnesses power from the environment or something, right? Maybe you're running a data center. Maybe you're just building a new desktop operating system, but you say, look, it has to be super duper secure or something like that. And this is the topic of our lecture today. So like, we don't know what's inside here, or we can kind of guess, but we don't really care yet. And we say, look, we don't really care about applications yet, but we can hypothetically think of, okay, we're going to run something meaningful. But the question is like, what is this layer of system call interface, or what kind of interface the operating system should provide? And that's the topic of these two lectures, today and next Tuesday. Right? Make sense? Okay, cool. And like, in a way, well, the system calls implement the interface of the operating system, right? And okay, sure, let's brainstorm for a little bit. Let's imagine we're designers of this new kernel. So what do you think you need? Like,
Printf is going to be a very common one.
printf?
Yeah, just any way to print text to the console or produce some other text output.
Okay, sure, yeah, print. And you say kind of like console.
Yeah.
But immediately one would say, okay, look, I want to generalize, because, okay, cool, that's nice to print to the console. And in fact, like, that will be ironic. This is the very system call which everyone builds. Even if you later on delete it, you just print it for debugging purposes, that something is running. Like, I have operating systems kernels which don't do anything, just print. But what I wanted to say, besides this anecdotal story, is that you probably want to generalize right away. You want to print not just the console, but just maybe to file. And again, it depends. So maybe if your device doesn't even have a file system, or your software stack doesn't have a file system, maybe console is the only meaningful way. Like, you don't need anything. But maybe you want to write something in a file, right? And I would say, let's just, for the sake of like sanity, like, and saying that we're not going to build something extremely esoteric, say that we want to have ability to read and write files, and maybe console. And I agree with this. So what else? What else do you need? Anyone besides gentleman in the first row? Second. Yeah, that's a great idea. So in fact, again, like, as I was saying, I build systems which don't do anything. They just do printf and start processes. Then I mean, you would say, okay, well, why? The reason is I want to publish a paper. There is a specific research objective, right? I need to run a benchmark. Benchmark runs as an application. So I need to start two processes and just do a printf so I can collect the data. That's it, right? So very realistic. In fact, common. Okay, start and stop processes. Say again? No. Okay, sure. Like, I don't have a good way to erase, but we can. Yeah, shouldn't be probably. Sub bullet will be. Okay, what else? Smart. Yeah, memory allocation. And can you elaborate? Because it's not immediately clear that it's needed, but can you try to guess why you would need it?
Because if you have still want then you the discrete memory or this one or
Kind of correct, but the answer I was looking for is slightly different because, and the reason I'm asking is that, and again, some extreme esoteric case, you might say, look, I don't really need to allocate memory. Maybe everything is static. But typically, the programming languages which we use, they provide us a mechanism to allocate memory, right? Not all, but many. Like, and there are generally three ways to allocate memory: static variables, like which are allocated when, like in a global data section, when the program is loaded, there is some region of memory allocated. On a stack, when you invoke a function, you have local variables on the stack, and typically you have something like heap, right? When you say new in C++ or malloc in C, right? Or sometimes it's hidden somehow, like box and Rust. It allocates memory in a heap. And that became kind of a de facto programming model. So you can imagine languages without it, as I said, like, but it's exotic, right? So, and memory allocation is mostly to support the language runtime. The language runtime say, okay, I need to allocate memory. I don't know what to do. But again, it's not always necessary. And it's a little exotic, but that's a good guess, right? And then what you said is that you say, look, but I would like to isolate between those memories of individual processes. And that's kind of hidden from you. Operating system doesn't explicitly, I mean, I'll take it back. Usually it just hides and everything is isolated by default. And sometimes you have a mechanism like a map to share memory explicitly, establish sharing later, right? Okay, what else? We will go like round robin.
probably often one way to kind
I'll put it here. I would say maybe, and I kind of agree with it, but it's so exotic that I want to put it in at the end. Clever. We want network stacks and of kind of like again, I would say not always, and x86 doesn't have a network stack, but I would vote yes for it, right? So in a modern world, yeah, you need some kind of a socket interface, essentially network stack, network communication. And one would wonder, why wouldn't you be able to provide a uniform interface to files and networks, like, and kind of like writing in a file is same as writing in a network. And it turned out that it's more natural to keep them separate. And that's why we have separate like file IO and network socket interface.
Start and stop threads.
Start and stop threads. That's a good idea. So we want, if we have processes, we say, look, guys, if we want to have multiple threads of execution within the process, we need threads. And I agree with that. Again, you can go long ways without them. So I will put minuses where for the interfaces which do not exist in x86, right? So I think x86 doesn't have threads and doesn't have sockets. The file systems we already have, so read and write files here.
some way to tell time.
Time. Why would you need time?
Maybe one measure stuff, maybe like your software doesn't have any view down for that. The operating system. Something needs to like the hardware obviously is like has some notion of time. So operator needs to relate it that machine notion of time to something.
Right. So I would say yes and no, because as you say, the CPU has instruction which counts cycles, right? So you always have relative time. And typically, I mean, not typically, but you can argue that, okay, look, if I want to have real time, I need to contact an external service and ask what is current time. And it depends. Like back in the days when networking was kind of less common, not all machines were connected. like locally, the system board was providing time, like BIOS was providing time. And then it was not accurate because based on the temperature, whatever, it runs faster or slower. And so people mostly switch to network-based time synchronizations. You kind of like send a packet and say, look, what time is it? And you play a protocol and you can synchronize. And then you synchronize once in a while, and then you can keep track of those local cycles. And then you can have very precise source of time. And the question is whether it should be provided in an operating system kernel or should be like a user level service is debatable, but I'll take it as a maybe. So it's a little exotic. So it's probably, I'll put it as a minus. Not because I don't like it, just because x86 doesn't have it. Any other ideas? But what kind? The what? You mean like, but no, like in a high level, without like any specific OS details, what kind of interaction with the hardware you want? Because as a systems designer, I might, and it might not be true, but I would push and say, look, we want to hide hardware completely, right? Because I want my applications to run today on this specific hardware and tomorrow on a completely different hardware, and nothing changes for the applications, right? So, but maybe you have something in mind. So what kind of hardware? We can come back to it. And there is truth to what you're saying, because sometimes there is always a trade-off. If you hide a lot of hardware details, you pay a price, typically performance. And sometimes people push back and say, open up the stack. We want a very specific application stack running against this hardware because we count every penny, every cycle. And then there's always like a debate about how much has to be hidden versus exposed. But we'll come back to it.
Okay, so this is system calls that the application would call to the system, or are you just talking more in general?
Well, I'm specifically, yes, like interface between the applications, like the system library and call here. So for example, if you invoke malloc here, you will have a memory allocator for allocating like small objects on a heap, right? But at some point you say, look, I need a large fraction of a heap so I can store these objects, right? And then you go back to the operating system and say, give me a chunk of memory. I will be allocating my small objects, or language runtime will be allocating those small objects. Does it help? So essentially, specifically this interface. And you say, look, if I want to read a file on a file system, I will open and read a file through this interface. And it's hard, like there is like a chicken and egg problem here. So as by the end of this class, and you will have some opinion about what has to go into the kernel versus what shouldn't go into the kernel. And if you stay in this field, this opinion changes. There is like a whole range of things, and there is always like a move up or down. So if you're moving things up, you end up building something what is called a microkernel. If you're moving things into the kernel, you kind of stick to the classical monolithic architecture. And there is no real single answer which is right. So it all depends on the use case. So everything what I say today is kind of relative to, I mean, I don't know what to your use case, but it all makes sense. It's also debatable. Let's stay on track. But just like what are the system call interfaces? Okay, you had an hour for that.
I would say pipes and signals for
That's very clever. You see, like we kind of forgot, like remember on my slide, I say isolation, everything is isolated. Someone mentioned like isolated memory allocation, but what about communication, right? So we need ways to communicate. So historically, people use this acronym inter-process communication, or IPC, and I will use it as well. So I will just put IPC for inter-process communication, meaning that processes in this system by default are isolated, meaning that there is like, it's not true in x86. It's not actually, it's true kind of. Okay, debatable, but like it's not always true that they are completely isolated, but in a very good design, they should be completely isolated by default. And then the operating system can grant them ways to communicate. grant meaning like ideally a minimal privilege to make sure that if one of those applications is malicious or maybe exploited, it can have a minimal effect on the rest of the system, right? But those inter-process communication mechanisms, and x86 specifically provides only one mechanism, which is called pipe, are needed, right? So, and it's good that you guys guessed that. So like I can put pipes here. Any other ideas?
Need something like radio.
Agree. So we kind of talked about it, start, stop processes. And you mentioned fork, and we'll talk about fork today. It's again, it's a highly debatable topic whether fork is a good idea altogether, but we live with fork just because it was a good idea 50 years ago. And today we inherited it. And like people are, as myself as a designer, I build a couple of systems in which fork is very, very hard to build, to the point that you like, just like, let's not build it and never think about it. Or let's say we have it, but never build it. Like, but yes, fork is one of those. Okay, actually the list is almost kind of complete. Like you guys probably guessed most of it. Any last minute ideas? Meters are typically hidden as well. Interrupts from hardware. So Unix has an idea of signal, so you can send an interrupt like software thing to a process to say something external is going on. Again, not always needed. x86 doesn't have it, but again, debatable whether it's a good idea, but I appreciate it. That's a good, like what you're saying is that, well, you guys talked about networks, you talked about files, but what about graphical user interface? And for many like years, I mean, not for too many, but at least initially, at least in x86, GUI kind of was equals to kind of console, like just basically text interface. And that was your way to put something on a screen. And I'll show you examples in a second in my slides, but obviously it's not true anymore, right? So now, like, everyone plays games, right? So I don't have a chance to play a lot, but ever, but still, but like half of why we buy a new machine is to get something faster on the GUI, right? On the graphical user interface, which actually resulted in a whole different stack. So I agree, it doesn't exist in x86, but it's a whole different beast. We wanted like, just because you can say, look, maybe I can hide it behind a file, but no, it's not fast enough. So you really need like a very fast stack to make sure that it's actually like works fast for you, right? So you're right. But again, not in this class. There will be no GUI, unfortunately. I will show you how a simple VGA driver works, but you will be disappointed. So it's all simple. Any other last minute ideas? It's actually more than I wanted you to guess. What is a serial input and output? Like, you mean like serial line? And yeah, it's typically hidden like behind the console, and I don't want to go into the details. So serial line is like a special port, used to be on the back of your machine, and you can connect the cable and read something on the other end of the cable. And sometimes when your machine doesn't have a GUI interface, or like in a data center, you just go around, plug those. Now these days, we usually buy like a piece of hardware which takes an input from serial line and then converts it into like a remote like network accessible thing, so you don't have to physically route those lines. But okay, sure. So you kind of, I mean, that was like very good. Like everything was guessed correctly, which is fine. And I mean, it's all natural, right? So there is no real like a reason to build something exotic. So again, if you want to build something very, 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 very minimal, imagine you hired to deploy a kernel on some exotic piece of software from today to tomorrow, or like within a period of half a year, but something has to boot like in 2 weeks. You really boot like, you say, look, I need processes, just creating, exiting, maybe waiting, maybe terminating, waiting on a process to finish. Some ways to allocate memory so your language runtime is happy. Typically files, but usually not on the first week you build files. usually end up building inter-process communication faster, and then you can build the network stack and stuff like that, right? Okay, sure. So that's all reasonable. And the question is, which we have to discuss today, is what kind of interface, like concretely, x86 implements, and in general Unix machines, and it's called POSIX, right? And x86, of course, like implements a very small subset of POSIX, but it's kind of inspired POSIX. But in x86, and it will be a little bit surprising. I mean, maybe not surprising to everyone, but what do you think was driving the design of the system call interface in x86?
Simplicity, mostly because they wanted to have something small that could be read in one semester.
But remember, x86 is actually loosely based on Unix version 5, version 6, right? So it was a real operating system which was used, like that was de facto operating system 50 years ago. That was what people were running. Today we're running Mac OS, Windows. They were running version 6, right? And they were like working with it. I don't think they were guided by simplicity. What was their kind of like, something shapes the interface, right? So, and I get it, it's a little hard to guess, but let's try to guess.
I would still say simplicity because Unix was born out of multics being too like complicated.
That's clever, and I agree with you. So maybe they discussed and decided, okay, let's like in general, the principle of simplicity and minimalism will allow you to like scale your software stack better. But I'm trying to ask something different, like okay, maybe you tell me.
Could we use something like
But okay, and I agree. Maybe the way I'm asking is a little puzzling, and that's why it's hard to find the answer. Like, imagine again, like you're hired to deploy something, like in 2 weeks, and 3 weeks, and in a month. You usually ask questions. Okay, what is the time I will be running on this machine? Because you say, look, I will, like you say, if I'm running whatever, some machine learning training applications, and I have to build the kernel to execute those applications. You say, and I have like limited amount of time. I will build a limited subset of system calls just to run those applications, right? I don't care about anything else at this moment, like, and simplicity comes naturally because you say, like, I simply don't have time to build anything bigger, right? So, but you say, look, it's all driven by applications in the end, right? Sometimes your research projects like ours, we can like, oh yeah, let's build something like completely exoteric, but it will change the world. Typically, it doesn't work this way. You're really driven by what is that you're running. And that's what essentially I was asking. What was the thing which those guys were running back then? And who can guess?
So a lot of Unix systems at the time were used for more scientific computation, given that, the computers were so expensive themselves.
Mhm.
So I would personally say that the system calls interface for flexibility and abstraction across different types of hardware.
Mhm.
That then there's a unified, well, not necessarily unified, but applications can run on different machines without worrying about underlying hardware.
Again, you're right as usual, but again, I will assign a historical video about these designers of the system, Unix systems, talking about it, and they kind of actually wanted to make it generic and available for all sorts of things. But what I was getting to is that their way of interfacing with the system, and like today, okay, like I interface with my phone with a finger, right? So like a couple of fingers. But back then they had this way of interfacing with the system through a shell. Like this obscure command, which you've seen multiple times. Many people say, okay, wow, I don't like it. Like, I do like it. I explain why. But essentially, for them, that was like they structured the whole system call interface around this abstraction of a shell. And if you ask yourself a question like, why? What the hell? Like, why is that? Who can guess why? What? Teletypes, exactly, because like this is exactly the hardware they had, right? So again, this is their environment. So this is two guys, Ken Thompson sitting, there is Richie standing, working together on the PDP-11 images from Wikipedia 50 years ago, 55. And their hardware, if you pay close attention, doesn't even have a screen. They have a computer runs programs, they have a kernel operating system, but there is no screen, right? And the way they interact with the system, they type something, some commands, and this thing prints them back. Well, that's the reality of life. Like in just in a handful of years, like 1980s, they already had a thing which had a screen so they can save paper. It's actually not a computer, just like a screen, a keyboard, computer sits somewhere else. This thing just dials in and connects to it remotely, right? But essentially, your world is restricted to, in their view, was to those common prompts. Essentially, the system asks you a question like, kind of like ChatGPT, what's the next question? But this is how it looked back then. And you say, look, I'll type a command, list all the files. And it does list all the files and prints them back, right? And you say, wow, can I do something smarter than just listing the files? Well, they have a tool like word count, which takes a couple of arguments and it can count number of lines in this file, right? And that was the world, right? And they said, okay, how to interact with the system? We're going to build shell. Shell was like you boot into a system and you see a shell. Today, of course, hardware is different, right? And we say, look, on my desktop computer today in the morning, that's my screen. So I kind of like, we interact with it with whatever, keyboard, touchpad. I still like running a shell, and I will explain why in a second. But like, depending on what you're doing, like sometimes you just, if you're just building slides like I am, like I just go ahead and like interact with a PowerPoint, right? I don't really need a shell. I just started a program. I mean, today we'll also open up a web browser, interact with ChatGPT or whatnot, right? But some subset of things are still can be done in a shell. Obviously, if we have a phone, we have a completely different user interface. We have a wristwatch, totally different thing. Android Auto on a car, like while you're driving, it uses just voice commands or something like that, right? So different interfaces. Essentially, the hardware dictates your interface with the system, and then it kind of like percolates and says, okay, what is the minimal set of system calls I need to implement? So if you're running machine learning workload in a data center on some exotic hardware, you have to deploy something from today to tomorrow. You say, like, graphical user interface, negative. Like we'll build like in 5 years after, going public, but essentially just like essentially minimal stuff to get the stuff running, right? And for them, it was shell, which, okay, I hope you can appreciate. There is this irony here. 50 years ago, someone didn't have a screen, didn't have a mouse, and they said, okay, we're going to build an operating system to run this thing, and we're still running it 50 years later. Like literally the same system call. And as I said, like some of those exotic quirks of the system call interface are not appreciated anymore, but we still have to kind of make stuff backward compatible and stuff like that. Question?
So another thing going back to how you mentioned that shell has kind of been around for like some 50-something years. If you look into how there's like TTY devices under Unix like operating system kernels such as Linux, that stands for teletype.
Yeah, that stands for teletype. Yeah.
That's
And
another-
if you ask me a question, do I understand how it works on modern Linux? Oh no, kill me. I don't want to understand how TTI works. It's not that hard, but it's like a game. Okay. So again, that's the major observation. So everything is kind of logical, but unfortunately we inherited from 50 years ago. Their hardware defined that they want to build everything as a shell, around the shell. And ironically, it's still a very powerful tool. Like I still use shell. In fact, I default on, even on my, like on all machines on which I have a keyboard, I default to a shell just because I mean, the things which I typically work on are, they're easier to make. It's more ergonomic to use a shell than anything else. I'm not very good. I've seen my students, it's like watching a movie, you're watching like on Zoom shared screen, person is so fast in a shell and do so many things. Like it's mind-blowing. And like you can watch maybe YouTube video showing this experience and just get inspired if you're not big fans of those shells. But I still like, for example, read my email in shell. I do my writing of all my papers in shell, LaTeX and stuff. I still use shell for my software development. As I said, okay, I'm kind of slow, but my students are blazingly fast. So I love it. But, you know, like what you do defines what you use, right? Okay, sure, shell. What is the shell? What is it? Who can tell me quickly what it is about? Is it like kind of characterize or explain me what shell is?
This is just like the textbook.
Text buffer?
Yeah.
Well, we've seen this command prompt when you just type something, right? But in terms of operating system, in terms of this diagram, which I keep drawing here, what is the shell? Where is it? Is it yellow part, green part? Yeah, and in fact, it does run in user space. So it's just a regular program, right? It runs like any other program, like I have it here on the screen, right? And it just uses the system call of the kernel to do whatever you want. And that's why we're talking about this interface. We say, okay, if you want to do something in shell and it's not yet supported in our system call interface, let's extend it by one extra call to make sure that shell can achieve whatever we want, right? So in general, it's just a regular application, right? And the user just boots into it, right? It's a normal process. Typically, the kernel, like in the days, you boot into a shell. Like right now, you boot into a GUI environment. Typically, in x86, shell is created after the kernel boots. Essentially, you boot into shell, and it's the very first program with which you interact. It's not the very first program in the system. There is like an init process, and then it starts the shell. But essentially, it's the first thing you interact with. And conceptually, if you think about it, like what you do there, it takes a command from you and executes it. And commands, those things, WC, it's not always the case, but in a classical case, and in case of x86, those commands are other programs in the system. So WC is just a binary in a system, and shell just executes it, meaning that it actually creates a new process which executes WC, and WC runs and outputs something on a screen, and shell is actually waiting on this process to finish. And when this process is done, it outputs the next command prompt saying, okay, I'm ready to do something next, right? And that's okay. That's kind of natural. It's kind of like GUI, but whatever on the keyboard. Conceptually, again, why it kind of survived all these 50 years is that it was designed as a minimal language interpreter. So, I mean, my default language interpreter today is Python, and probably yours too. If I want to do something fast, I open up Python, and just because the ecosystem of the applications or libraries is so rich that I can do almost anything, like open a CSV file, do some stats on it, whatnot, right? But for them, they said, okay, look, we need kind of like a minimal language, which allows us to compose like ecosystem of small applications. And essentially their way of composition, because they didn't have like a full language or like types or anything, they said, okay, these strings or output of one program will be redirected to the input of another, but then you can compose. And okay, you say, okay, well, that sounds crazy, but I'll give you a couple of examples from like modern world, from Google. So essentially, like again, all these things like PS lists all the processes in the system. Grep searches for a line essentially in the output of PS. AWK is a more general like interpreter in a language. Xargs just executes this command, so maybe not. And this thing is a pipe which essentially connects the output of this command to the input of the second one. Then since you use another pipe, you connect like them. And essentially here it finds all processes running, all processes with the name Python, and extracts their process IDs with this second column, and just kills them with this command, right? And again, you say, look, but that's pretty cool because none of these commands is designed to kill, like besides kill itself, but kill can only kill one command, like it's kill process ID, right? And this kind of like tiny language allows you to say, look, I will kill everything what has Python in the name, right? It's kind of cute. You can do all sorts of things. So like this one parses the web server log file to extract the first field IP addresses. and counts how many times each IP appears and shows the top 10, right? So here is like top 10, sorting, checking for uniqueness of this IP, sort function, this cuts the field, and this is just accesses the log, right? And imagine, like, again, it's, if you, like, I still use it often today for, like, I like to interact with the system in this way. I like to manage my files through the shell, whatever. If I search, I mean, by now I have like dozens of failed and successful papers, and I search for a specific phrase in them. I can do this, right? I don't have like a search database set up on my machine, right? So that's just an insight, like kind of a motivation for why it makes sense. And it does make sense. And that's why it survived 50 years. So Shell was like a very ergonomic tool and very generic tool, not just for scientific applications, for everything, for text processing. As I say, my text workflow is makefile plus LaTeX plus whatever, a bunch of text files, right, which I edit. Okay, any questions? Okay, before we all fall asleep. So our goal is to figure out how to design Shell in such a manner that we can support those pipes and other features to kind of like allow to compose programs together. Like the whole idea was this composability. By the way, this idea disappeared in Windows for a while, right? And they said, okay, we don't need Shell. Everything will be graphical user interfaces. And you were, I mean, I'll show you in a, like, here's my slide with Windows if I still have it. Where is not this one. Like everything in that world looked like this. And either way, I mean, like on Android and Apple devices, like on GUI heavy centric devices, it still like looks this way. You have to, the application has to support everything. If you want to search for a substring, then you have a bunch of text boxes and you have to click them, because if you want to be unique, there might be like a checkbox saying, okay, like figure out only unique substrings, right? But in that shell-based ecosystem, you can compose small things like in a language, right? And then Windows said, okay, well, it works, but you know, we're kind of tired of all this like tiny little boxes. So they implemented a PowerShell, and now it's again, in general, they kind of adopted the Unix style ecosystem, partially at least. Okay, so anyway, so our goal for now, until like for the next kind of this and next lectures, to figure out what kind of system calls we have to provide to make sure that this thing works, right? So we're kind of going back to the system call interface and take a system call centric view, but with the goal to build a shell, right? Okay, and this now it becomes concrete. So this is the system call from x86, concrete syntax which it takes. It's similar to what Unix takes, like POSIX takes. But essentially, we start with like, okay, we want to open files and read them. And you've seen this, right? So because you were in 4400, so the way to open a file, or specifically ls.c in a read-only mode, the running system implements an open system call. It opens the file. A little unusual, it returns you something called what is called a file descriptor. So again, debatable choice, but sure. But what is it? So who can tell me? What is this file descriptor?
Just a,
Correct. And what's the role of this integer? How is it used by the system?
It indexes files which maps to actual files.
Correct. Let me show you a picture. So, and let me explain why this choice actually makes sense. So open returns you a number, like let's say number 3 in this example. This number makes sense at user level. And this is the kernel. Of course, the idea is that this number will allow you to refer to the same file in the kernel file data structure later. But you cannot really return a pointer, right? Because those two address spaces are isolated, right? You cannot use a pointer across the address space boundary. Otherwise, you know, like you can implement it, but then it comes like exposes you to all sorts of attack. So it's kind of like an abstract pointer, which says, okay, it really points to a file, but really it's represented as the number, which indexes in this table, file descriptor table, and this table will contain a pointer to the file data structure. the idea is that you open a file, you get this pointer. Like if you have a high level language, you can hide everything and say, look, this is the pointer, but underneath you will be invoking this system calls. And later on, you say, I want to read from this file, and you provide this pointer and you read from this file again, right? Make sense? But this is how you kind of like isolate address spaces and say, look, and this number only makes sense in the address space of this specific process, right? Because the other process will have its own file descriptor table. And so, for example, here you're reading from number 3, it points like indexes in your own file descriptor table, which is per process indexes in a file, and then file system like figures out how to really read something from disk, right? Based on this data structure. Here, I mean, I can either put 3 here and they can either point to a different file or maybe to the same file. It doesn't matter, like really. But here in this example, you have each process will have its own file descriptor table. Just for the sake of example, this one returns 4. So this entry into 4 points to the file, which is wc.c, right? And so those, in a way, the whole story about file descriptors is to kind of implement a pointer across address spaces. Like you can come up with a different example. You say like, you have a distributed system, 2 different machines, and you say, I want to open a file on that other machine. That other machine says, yes, I opened a file, like you know it as number 3. Next time you want to read from this file, use number 3 and I will read from that file and it's yours, right? And so that's how it's done. But this is across the kernel and user space. Go ahead. Yeah.
The file also add file.
So again, this command?
Yeah, like the first argument is the name.
Yeah.
But the second.
No, this one is just a flag saying, I wanna open this file for reading. Open read only. You can say, you can compose these flags and say, open read write, open append to a file, stuff like that.
But the file descriptor.
And the file descriptor, this is how you remember a specific file, although it takes you kind of like through a level of interaction to say that the kernel later on, like when you read from this file, providing the same file descriptor, it will just go through the file descriptor table again, and it will point to the same file. And like essentially, that's the way to refer to the same file, but across the address space, right?
Okay, so the question, did the file descriptor table have the flags inside of it?
No, file descriptor
Versus
table.
versus
Typically, and again, just imagine you programming it. You say, well, I really need just like, when my code here, like this code in a kernel just needs a pointer to this data structure. And you can say this one as a read only flag, for example. You can put the flags here. You can also put like position within the file, which is called an offset. So because you start reading from the beginning and then you say you consecutively read and you keep track of where you're reading, right? And so this data structure, like everything is written in C in x86, right? It's just a C struct. You can add any fields, right? But user like invokes a system call and then 10 milliseconds later says, okay, I opened a file, and 10 milliseconds later says, okay, read something from that file, from this specific file which I opened before, right?
But what if you have like 2 processes opening the same file?
Great question. So then, yeah, that's a great question. So let me just explain it. And in this case, so for example, some number in this table, it can be the same number or it can be a different number, will be pointing. For simplicity, I can say that it will be pointing to the same file data structure. In practice, no. In practice, just because you have different offsets within the file, you might be reading from different spots. The way it will work is that it will create another file data structure here. We'll have a pointer like this, and then these 2 data structures will refer to a single, something what is called an inode. It's a file on disk without a name. In fact, you can know the same file on disk under different names, and you can open, you don't even know a priori whether ls.c and wc point to 2 different files. It's just 2 different names, which you know, right? But this is how it will be implemented. So there will be two different file data structures, two entries in file descriptor tables, but they potentially can point to the same inode, right? Make sense? Any other questions? And I mean, we will read the source code for how it works later on in the class, or towards the end, because we'll get to file system towards the end.
Scripters, if pass it, or
Say this again. In some language runtime, or like in a modern POSIX interface, they're like combining file descriptor with some additional flags or something. Here, like this is, and I mean, you can, this interface is what x86 implements and what Unix POSIX implements, most kernels implement underneath, right? If your language runtime, let's say Rust or something, or even C++, they say, look, I like this number, and the lowest bit of the number will be a file descriptor, and the top bits of the number, or top bits of this number will mean something else. Then that's your choice of your language runtime. But I think when you're passing across this interface, if I remember, in x86 at least, it's true for sure. In Unix, I think it like just means the number. But I mean, you can catch me wrong. I not like if you have a specific question, like follow up on Piazza. By the way, I forgot to say, like sign up on Piazza. I created Piazza, and all our communication will be actually like questions, answers. Not all, but it's convenient to have it on Piazza, right? And I will try to read and answer, and I ask my TAs to read and answer questions on Piazza in real time. So university doesn't allow us to use Discord. It's kind of like according to some firma, whatever rules, right? But Piazza is allowed, so that's the best we can do. So I created it. Canvas is created. Piazza is created, right? Stuff like that. Any other questions about file descriptors? Well, no, not exactly. So it will become clear towards when we think of these three colors as three different address spaces, like blue, green, and yellow, and they're not shared. In yellow, it's the same address space. So you can have like two pointers, pointer 1 and pointer 2, one pointing to this, one pointing to this, stuff like that. It's like, it's a regular, kind of like the kernel itself looks like a regular C program. Like there's nothing surprising about it. Data structures, pointers, everything, right? The fact that it's written in C, again, back then the C was the language. There was no better language. Now we have better languages, so we can write it in any language we like, right? Does it make sense? Okay, but it will become clear again. Okay, all good for now? Okay, let's move. Okay, sure, files are easy. The next suggestion from you guys was, okay, we want to print something into the file or on the console and stuff. And so those guys came up with the following idea. They said, okay, we'll have a convention that the first three file descriptor numbers are magical. They have special meaning. So 0 is the standard input. So if you don't care about doing something special with 0, typically input comes from a keyboard. So essentially, like when you say read something from 0, it means that the person will be typing on a keyboard. When you say write something to 1, it's a standard output. It means that it will show up on a console, right? Like typically it's in a shell, but of course, like it depends. Like if you're running a real piece of hardware, it will show up on your screen, right? And 2 is a standard error. So whatever, if you encounter an error, you print into 2 or you write into 2, right? Make sense? And okay, you say, okay, why is this convention? It makes sense. Let me explain it in a second. So again, just for illustrative purposes of how it works physically in x86, in a typical case, when you're reading from 0, instead of going to a file here, you kind of like, it's kind of like a type polymorphism. You say you implement a different data structure, and they say it's actually not a type, it's a console. And really, like if you're trying to read from it, it will wait for the input from the console, from the keyboard, right? Make sense? And it's okay, sure. And the same from like if you're writing something into one, your file descriptor one will also point to this console abstraction called console data structure in the kernel, and it essentially goes and like shows up on your screen, right? So essentially, that's the way to communicate with the screen. And just to illustrate this idea, if you have a very simple program which just reads a file, so we saw it in this pipeline here, which I was using as an example. This cat just reads this file from, like here it reads from a file, but if you just read from a like what cat does inside, which is kind of beautiful, is that it reads from the standard input and writes to the standard output. But those can point to different places, so it doesn't have to point to something specific. So just to make it again, just like just an inch more concrete. So here, for example, that's our website for the class, right? So if I go here and I switch to like I do ls or L, I like L, and then I cat the index file, like this command cat, sorry, like it's small, probably, but get larger. Like it still exists, and it just like outputs on my, it read from a file, like it just, there is a special mode, right? But it output on a screen, right? And that's the web page of our class, right? So it's all commented out, but really the header, you can recognize, okay, name of the file, it's all MD, right? So this is the command. And really just implementation of cat in x86 boils down to those lines which I just showed on the screen. So this is the loop, and the loop, what it does is it just literally says, okay, sure, I will be running an infinite loop. I will be reading from standard input into a local buffer of 512 bytes. And I pass it to the system call, because system call says, okay, I want to just read that much. System call says, okay, like it doesn't know the size of the buffer. It will just copy data into it. You say, if nothing is read, then okay, sure, there is nothing on the standard input, so I'll break out of the loop and I finish. If we're at less than, if it's a negative number, the convention which they came up with, which is not ideal, but that's a convention. They said, okay, if it's a negative number, then there was an error reading something, and they output the fact that they encountered an error to the standard error descriptor, and then exit the program. But if everything went okay, and I read 512 bytes or less, maybe this number can be less than 512, you just write it to the standard output, right? And you say, look, there's a buffer, there's how many bytes I read. If this one fails, you again print an error and exit, right? But it's kind of like, okay, sure, it looks elegant. You say, look, it's a powerful command. I can like read the file. It's not that I'm opening a word processor. It's just a loop which reads from standard input and prints the standard output. Question. Oh, I had somewhere. Oh, sorry. Like I probably copied this from the slide which discusses fork. Just forget about it. I should fix the slide. You'd never seen it. Any other questions? Again, one powerful observation, that this kind of convention, it's almost like you're writing, I mean, again, back then, and to some degree now, the boundary between the language runtime and the operating system kernel is a little blurred. Right now, for historical reasons, we got stuck with this POSIX interface, and we say, if you want a language like C#, it has to run on top of like Windows and POSIX, so whatever, but build whatever. If you have some exotic features, and you can build those pipes in a language, right, or something, right? And maybe those pipes can like send commands to the data center or something like that. And in their case, they said, okay, our interface is designed to write commands like this, and it kind of looks elegant. So they say, look, it's very minimalistic, 0, 1, 2. Everyone remembers those numbers. And so it looks nice in the language implementation that you see back then, right? Okay, sure, we got the input output, right? Now they said, okay, next turn, creating processes, obviously, right? Like it's actually was line number 2 on your guest list. Okay, here, the choice of how they create processes is a little esoteric. But let me explain. They came up with this idea. They're gonna implement a system call which is called fork. It's completely it's counterintuitive as hell how it works, right? Fork is a system call, right? So like I said, it goes into the kernel and kernel does something. Specifically what the kernel is doing, it actually creates an identical copy of this first process. The only difference between them that inside the first process, which we'll call a parent, the ID of the second process, process ID. So this process is created as process ID 32, and PID of this process can be like, I don't know, 17. The fork returns 32 here and returns 0 here. That's the only difference, which if you ask yourself, like, it's just one register, or in a 32-bit calling convention, it may be one value on the stack, right? Which is different between the two address spaces. So if you have some data structures here, if you have a pointer P pointing to whatever, a tree or a list on the heap, right? The same P will exist here. So they are completely identical. Make sense? It just clones them. I mean, you'll know this, right? Sure. Why is it even good to create a process like this? This is puzzling, right? Okay, sure. So this is an example of how you use fork. So you say, look, I will invoke a fork system call from C. It returns a process ID. If it's greater than 0, then it means that I'm in a parent. Sure. You say, look, I will just be waiting, and I will wait on the parent, on the child to finish. Then I will print that child is done, and then I'm done with this code, right? If my PID is a child, you know that you're within a child, that it's like this code is executing, right? You say, I am a child, I'll just exit. And there might be a chance of error. Maybe the system ran out of memory and it just cannot create a copy, right? Or something. And you say fork error. So it's a negative number, actually, right? Makes sense? That's the way to invoke fork.
Just as an example.
Yeah. We will go through the code for fork. Actually, we'll go more for, I think, through exec. Fork will be like a homework or something. But yeah, so this is how you use it, right? Sure. Let me ask this question. So why do you think it makes sense? Because it doesn't make sense, right? But tell me, why does it make sense? Anyone?
Is it because that way, the same process, then you still have access to stuff like different parameters that might have been available to begin with, that then you can feed them in the time. Like, for example, if you launch a program using Shell makes a fork of itself before starting up that process. And because you were starting that process through the shell, you enter potentially some arguments through the command line. So those are still accessible.
In a way, I agree with you. I guess that, like, it's hard to capture, like, I have to rephrase your explanation, and I will use it like next 10 slides to do it. But let me take another version.
Correctly, it's so that pipes are easy to implement from like a user space shell, because you can fork and then you can set up everything you need for the pipe, and then you can exec to change it to a different program. If we have like theoretically a combined fork exec which didn't like do the fork first, then you wouldn't be able to set up that process communication.
Correct. And it's kind of like exam level answer, which is like correct. Okay, sure. Let me explain for everyone. Like, again, if you ask me why this choice makes sense, there's no real reason. It's just like it's completely loony. It doesn't make any sense. Like, why would you, like, really, I want to start Apache, but I first have to fork myself and then do something to turn it into Apache web server, right? Sure. They had a way for this. They came up with the second system call, which is called exec, right? And exec replaces the address space of a program with another program. So which means that the sequence is you first do a fork. Inside the parent, you start executing your code, like whatever, do whatever you want. Inside the child, and typically it's a shell, but it doesn't have to be a shell. It can be any program. Where a fork returns 0, you invoke exec. And with the argument, for example, bin/wc, and exec drops into the kernel, And unless there is an error, it will never return and execute this line. It will just scratch this address space completely and replace it with WC, and will start execution from the entry point of WC. Right? Completely sure. Like you first want to create a clone of yourself and then kind of completely reload it with something else. Okay, but at least we know how it works. And it seems that you can, it seems working. Why not? You say, look, I will fork, I will exec, and then this thing will turn into WC and will run a main function of WC. So the end result is like you had shell and you kind of created WC here, right? Make sense? But again, why go to all this kind of trouble of first creating a clone of a shell in the middle and then creating WC? And again, it's debatable whether it's a good design choice, but for them it worked and they wanted it this way. And the reason they wanted to do it is they wanted to support higher redirection. Question?
Yeah, just to.
No, it's a completely different address space, like a new process. Uh-huh. Okay, let me go over it again. It's important to understand, and we'll understand it in details. But first, let's understand it like this. So it's kind of like a call. Sorry, it's a call into the kernel, and logic of fork in the kernel creates a new address space. Like it's a new process. So this was process P1. This becomes process P2, which means that the kernel probably has list of processes, and now there will be a new process on this list, right? You can pass it to a scheduler, you can context switch in it later, but it's not ready to run yet. And what the kernel is doing next, initially this address space is empty, but it just does a bit copy of whatever was in the first address space, in the parent address space, into the second, and just says, sure, I will return and start executing in both address spaces. I will start executing at the line, like physically. One way to implement system calls is to invoke an interrupt with an int instruction. And in both of these, the next instruction after the int will be some instruction, and it start executing from that instruction. And the only difference between these two address spaces is that in one of them, the return value from the fork is 32 because it's the process ID of this new process. So this one should be called process 32. And in the second one, it's just 0. But it's a bit copy, like all the pointers, everything. Like if you're about to crash here, you have a bug, you will crash in both if you execute the same lines, right? So it's all identical. It makes sense. And exec is a trickier business. Exec says, okay, sure, I will in this child, I will again call into the kernel, but instead of returning, you can return if there is an error. Somehow you say exec. Like instead of WC, you wrote something WC3 and it doesn't exist. And exec says, okay, I cannot find a binary. So then it will return and start executing. But if there is no error, it will just clear this address space completely and will reload it with the binary of WC and start executing from the entry point. Make sense? Everyone makes sense? It's kind of important on this.
So if you fork and then exec, is that pretty expensive to recopy the address space and then do it again?
It depends. It's a little expensive. Yeah, I agree with this. But again, if you stay in this field, people will start telling you, oh, there are ways to optimize, And Linux these days you can explicitly say, I'm gonna exec soon. So don't even copy the address space. Don't bother, just whatever. The next couple of instructions is enough and I will do exec. So they have all sorts of optimizations these days. But yeah. But if you do it naively, like x86 does, then it's expensive. You first create a process, you copy the address space, and then you immediately throw it away. It doesn't make sense, right? Any other questions? We're good? Okay, the reason they did it is they wanted to support this idea of IO redirection. And this is kind of what you guys were talking about just a second ago. okay, let me just give a gentle introduction to what it is, but we'll run out of time pretty soon. So what is this IO redirection? The idea is the following. You remember my cat example. So they say cat just simply reads from 0, writes to 1. Okay, sure, that's how the cat is written. And they said, okay, that's a powerful mechanism. They say, if you want to count the number of lines in ls.c, that's your command, right? And it outputs on a console. You ask yourself a question, okay, what if I want to save this number in a file? Well, you can always do something like, okay, sure, let's do additional arguments, kind of like an output into a file, but this becomes kind of annoyingly cumbersome, right? So you say, look, is there a better way? And they came up with this idea. It's almost like an operator in the language, right? They say, look, this operator will be redirecting output into a file. And that the program itself doesn't have to be changed at all. It doesn't even know where the output is going. It doesn't need a new argument like -O. It's just like the shell itself sees this symbol, parses it, and says, okay, I will redirect the output of that program into something else, right? And sure, and they said, okay, sure, we will support a couple of those operators, like redirect output, redirect input. And so, for example, here, cat, for example, redirect output of ls.c into ls.new, and it effectively copies a file, right? You redirect input, you say wc minus l, but please take input from ls.c. That's the same way of writing wc minus l with this argument. Same for the cat. And of course, you can redirect both, and it's your shell implements it. It's kind of like a tiny language. So you say, look, wc takes an input from ls.c, output into the file foobar.txt. And they said, okay, sure, we want this idea to work. How to build it? So at the level of operating system, they came up with the idea that it will totally be fine if we make sure that this standard input and standard output in a file descriptor table, instead of pointing to a console, point to a file. That's, it was a little bit of programming practice or like magic. You say, look, that's my whatever, my way of implementing polymorphism, right? So it's like same interface, just different behavior. But fine, so that's easy in the kernel, right? As like you say, look, like just like if this is true, then like you reading from file and writing into a file, and of course they can point to different files. That's fine. It allows them to essentially like, but really now it becomes a language. So you can say, look, I can read from a file, read from a console, write to a file, write to a console, or by the way, I can write my output goes through a pipe to an input of another program, right? Makes sense? And so, but nothing changes in cat. Cat is the same. So it just like nothing needs to be changed. It just like still reads from 0, writes to 1. But the shell does the magic. And now they had a problem. They had to solve this. Like they say, okay, if I have a shell which takes an input or output redirection command, I need to somehow implement this business, right? And essentially, this will justify the use of fork, then some changes to the file descriptor table of the child, and then execing, because exec will preserve the file descriptor table. But let me stop here because I'll run out of time halfway through this idea, and let's better like start on Tuesday next week, and we will just finish at system call interfaces. So thank you guys. I'll see you next week.